All right, guys, welcome back. I apologize for the delay. I had some technical difficulties in recording yesterday, so unfortunately, we had to take a break in the middle of that. So we're back now. We have just come back from doing some building formulas from compounds with the following ions. So that's where we were. We took a break from there, and we are now coming back to talk about molecules and molecular compounds. Now, when we talk about molecules and molecular compounds, we're talking about things that are made from nonmetals. So remember, when we're looking at our periodic table, we're focusing on the upper right corner of this table. So bonds between, say, nitrogen and oxygen, carbon and oxygen, nitrogen and sulfur, things along those lines. So everything that's up in that right corner of the table. Okay, and they can be the same element as the O2, which is a diatom. We have two oxygen molecules bound together, or they could be different, carbon and oxygen, which is carbon monoxide. Okay, we use their atomic symbols and subscripts to convey the proportions of the compound. So I know exactly what's in it. That's given by the atomic symbol, and how many of them there are, which is given by the subscript that tells me how many. Okay, so we always know what we're talking about. Now, I've alluded a couple of times to the fact that there are some things that always appear as dimers when they're by themselves. So there's always two of them when they're by themselves. Things that appear like that, okay, are typically gases. So we have nitrogen, oxygen, fluorine, chlorine, bromine, and iodine, as well as hydrogen. So they make this nice little 7 on the table. And of course, if I turn this off, carbon, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine, and then hydrogen. Those are the ones that appear as dimers. You are responsible for knowing that. It becomes important when we start talking about balancing equations and writing those kinds of things. So you will need to know that. There's a little mnemonic that we use to talk about it, and that's have no fear of ice cold beer. So the have refers to the hydrogen, the H2. No is for nitrogen. Fear is for the fluorine. Of is for oxygen. Ice is for the iodine. Cold is actually for the Cl. And then beer is for the bromine. Okay, so that's what we're talking about when we talk about that. Right? So that should help us remember. Again, I like the fact that it makes this nice little nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. And if you count that, 1, 2, 3, 4, 5, 6, and then hydrogen makes 7. So it's almost making a 7. It looks like a 7, but that 7th one is the hydrogen that we have to pick up. Okay, so those always appear as dimers when they're by themselves. That doesn't mean that they're always, two of them when they're bound to something else. So CO, carbon monoxide. I don't have CO2, although I can have CO2. So this one is carbon monoxide, 1 oxygen. This one is carbon dioxide, 2 oxygens. Okay. We'll talk about the names for these things in a bit. All right, we're going to get to that today. So those are the things that we're talking about when we talk about those. Now, our molecular formulas, again, tell me exactly what's in it and how many there are. So for something like H2O2, that's hydrogen peroxide. We call it hydrogen peroxide because there's 1 hydrogen for each oxygen. So H2O2 means 2 hydrogens, 2 oxygens, 1 hydrogen for every oxygen. So hydrogen peroxide. That's a molecular formula because, again, I have 2 hydrogens listed, 2 oxygens listed. I know that that represents how many there are in that particular molecule. We also have something called an empirical formula. Now, an empirical formula is the smallest whole number ratio of atoms in the formula. So I can't break it down any further. When I look at H2O2, what I see is that both of those can be divided by 2. And so if I take my H2O2 and divide that by 2, that reduces to Oh, and so this is an empirical formula because it represents the smallest whole number ratio of the hydrogen and the oxygen. And of course, that means that this is a molecular formula. And it tells me exactly how many of what are in that formula. Okay, so we should be able to look at something and say, okay, if it's divisible, then it's a molecular formula. If I see that I can't divide it, it might be a molecular formula, it might be an empirical formula. It's hard for me to know. Okay, so there's no real way for me to say. All right, so we need to be able to look at both. It's important that we can determine what the empirical formula is. We need to be able to get to molecular formula from an empirical formula. Our empirical formulas, and I'll talk about that in just a minute. One other thing I want to talk about before I get to the empirical formulas. We need to talk about molecular models. So if you go out into the internet to look at descriptions of some of these things, there are many different ways that you might see them talked about. So you might see a molecular formula for hydrogen, H2, for water, H2O, for ammonia, NH3, for methane, CH4. Okay, so those are molecular formulas because they tell you how much of what is there. Okay. We might see a structural formula, which shows me that H2 contains two hydrogens with a bond in between them. H2O contains a hydrogen bound to an oxygen bound to another hydrogen. So it shows me the order in which they're bound. Okay. It shows me the geometry in which they're bound. So I can see what's bound to what. So NH3, I can see that nitrogen is bound to all three hydrogens. CH4, I can see that the carbon is bound to all four hydrogens. Okay. That may not always be obvious to us. And a molecular formula might be something where they aren't all bound to each other in a way that makes sense. Okay. So they aren't necessarily representative of what that structural formula would look like. Okay. So a structural formula will show you exactly what is bound to what. We can also talk about a ball and stick model, because even though I can write a structural formula like this, it doesn't necessarily tell me what it looks like in three-dimensional space. It's very flat. It's two-dimensional. So I don't necessarily know what it looks like in three-dimensional space. So it can help, but it's not necessarily as helpful as maybe it should be. And it depends on what I'm trying to do, whether or not I need to know what it looks like in three-dimensional space. So if I'm trying to determine if I can do some chemistry with something, I need to know, can I get in there to attack this thing or not? And of course, looking at this model, I can tell that I have some space to be able to get in there to attack it because of the arrangement that it has. Here, it's a lot more crowded. It's harder for me to get into that central atom to do some chemistry because there are four things around it, and it's very hard to do so. Whereas if I'm looking at it like this, you're like, oh, well, I can come from above and I can come from below. And that's not really what it looks like. Okay, so it's important to understand that three-dimensional geometry. That is something we will get to just before the third test. It's on the second test, but just before that third test, we'll talk about what those geometries look like and how we predict them. Okay. We also have something called a space filling model. And this space filling model is based on the idea that we have these two things and they're bound to each other. And those electrons take up this statistical distribution around the center of that atom at any given time. So it shows that statistical distribution around the atom at any given time. So it'll show you where the electrons might be at any given time. Okay, that's what those space filling models are meant to represent. Okay, so it's helpful for us to be able to understand where in space, how much space that thing might take up, and how much space we are looking at for those electrons. Like, where are they if we're trying to do some chemistry with them? Are they going to be available to us in a given region? Can we get to them? Can we see them? That kind of stuff. So there are very different ways that we look at these things, and all of them have their time and their purpose and whatever. But if you don't know what they are, when you see them somewhere out in the universe, you might be like, I don't know what that means. I don't know what that is. I don't know how to deal with that. So I wanted to show you how these things, what they look like, how they're representative of the molecules that we might be talking. Okay. So that's what we're talking about for those. That's generally how we see these things. Right? Now, let's talk more details about our empirical formulas. And remember, I said that those empirical formulas are the smallest whole number ratio of atoms in the molecules. And I mentioned H2O2, which is a molecular formula, because it tells me that it's made of hydrogen, it's made of oxygen, and I have 2 of each. Okay, that is a true formula. So it's a molecular formula. It represents the molecule that is that compound. Okay. When I divide that by 2, I get the smallest whole number ratio, which is HO. That's the empirical formula for that particular compound. Those formulas are typically determined by experiment. So we can take this thing and put it into what we call a calorimeter, and we can burn it to understand, okay, how much of what components are in it. And we can get a relative distribution of how much of it is there. So I can see that half of it is hydrogen, half of it is oxygen. Okay, so we understand that that empirical formula must be 1 H and 1 O. We'll talk about how we do that as in a bit. Okay. So we need to know how to determine an empirical formula from a molecular formula, and we'll figure out how to do it in the other direction a bit later. Okay, so first we're going to figure out how to find an empirical formula from a molecular formula. Right? So I want to do some practice. So I have some molecular formulas that I'm giving you here: C6H6, N2O5, C4Cl4, PCl5, and C6H12O6. These are all molecular formulas. And I want to predict the empirical formulas for those molecules. Okay, so I want to predict what is that empirical formula. That lowest whole number ratio. And so what I want to do is divide so that I can't divide any more. All right. Let's talk about this first one. I've got C6H6. I can divide this whole thing by 6, right? And if I do that, I end up with CH. So that CH is my empirical formula. And I got that by dividing by 6. And so that's that number that we need to multiply to get that molecular formula back from the empirical formula. Okay, so it's our factor that we use to get the molecular formula from the empirical formula. Okay, so that's what we're talking about. Now, is there a factor that I can use for N2O5 to get to an empirical formula? I don't think so, because if I divide this by 2, then I end up with 2.5 here. I can't divide 2 by 5, so I can only divide this by 1. And that means my empirical formula is N2O5. Sometimes we find that that molecular formula is also our lowest whole number ratio, and so it's our empirical formula as well. And so what I told you was that looking at a molecular formula, I may not be able to tell you if it's molecular or empirical. And this is what I meant by that. Sometimes it's both. Okay. So looking at our C4Cl4, is there any way I can reduce that? I think so. Yes. I can divide by 4 and CCl, which is that lowest whole number ratio. And if I multiply that by 4, I get back that C4Cl4. Okay. Let's look at our PCl5. I can't do anything with it because that P is a 1 and the Cl is a 5. So I have to leave that as it is. And that means that it's PCl5 for my empirical formula. And my factor is 1. That's all I got. All right. Now, looking at C6H12O6, I can divide this by 6. When I do so, I get a CH 2, and so that's my empirical formula. That's the lowest whole number ratio I can get out of those guys. And if I multiply this by the factor, by that 6, I get C6H12O6 back. So I asked you, what's the relationship of the molecular formula to the empirical formula? And that's what I mean by these numbers. That's that relationship that I was talking about. And what number do we have to multiply? And that's, again, the relationship that I was just talking about. What is that factor that we're looking at? Okay. So questions, comments, problems on how we move between the molecular formula and an empirical formula. Cool. Okay. So let's practice some more. So I'm giving you a table. I've either given you a molecular formula and I'm asking you for an empirical formula and I give you the ratio, or I might have given you an empirical formula and the ratio and I want to know the molecular formula, or it could be that I gave you a molecular formula and I want to know what the empirical formula is and the ratio. So you're filling in the rest of the table, okay? So I want you to take a moment, fill in the rest of this table. And I'm going to work with you to do exactly that. All right. Now, this first one, C6H12O6, this is glucose, and this is one we actually just talked about. So I know if my ratio is 6, so I'm dividing this by 6, that means I end up with CH2O. That's what I end up with for my empirical formula. Now, if I have an empirical formula of CHO and the ratio is 3, I multiply everything in this formula by 3, and I end up with C3H3O3. Okay. Looking here, I have a B5H7, and the ratio is 2. So I multiply everything by 2, I end up with B10H14. That's my molecular formula there. Now here all I have is this C4H2O2. And I recognize in looking at this, I can divide that by 2. And so the factor I'm going to put here is 2. When I do that, I end up with C2H. Okay, so that's my empirical formula for this particular grouping. I have an empirical formula of CH2, factor of 2. So I'll multiply everything by 2, and it gives me a C2H4. Okay, so that number applies to everything. And right here, I have a C4O2. I can divide everything by 2, so I'll put that 2 right there. And that one's going to C2O. Okay, so that's what we're looking to do there, is to fill in the gaps in that table. And I can do that fairly easily with the information that was provided. Questions, comments, problems on that? All right. Cool with that. Okay. So let's see what's next. Now we're going to come into name. So we've talked a little bit about empirical formulas and molecular formulas. We will talk eventually about how we can calculate those things. We're not going to do it this time. We're going to do it in the next lecture. Now, naming ionic compounds. We need to be able to name things. And that's because I'm going to throw a name at you and expect you to write a formula. You may have a formula and you need to know the name. Both of those things might happen. Now, how do we name ionic compounds? Remember, ionic compounds are metal to non-metal bonds. They're based in the charges for those things. We always name the cation, the positive ion, which is the metal, followed by the name of the anion, the negative ion, which is the non-metal. Okay. The name on our anion is going to change to an IDE. So a chlorine becomes a chloride and oxygen becomes an oxide. Okay. And we indicate the charge of our cation in parentheses and Roman numerals if required. When is it required? Anytime it's a transition metal. So if it's in the D block or the F block. So here or here. It is not required to do it for our main groups are S or P's, not required. Now, is it wrong if you do it? No, absolutely not. It's not, but it is not required. Is it wrong if you don't do it for a D or an F? Yeah, it absolutely is wrong. So if you don't do it, it will be points taken. It's partial credit, not complete credit. Okay. Now there are common names for these species. So let me show you what I'm talking about. We'll open our exam handouts. And this is a slightly different version of the exam handouts that you guys have. I found an error and I fixed it. So there are some common names. So we're going to scroll down and find this table. It says common names. And that's right here. So on this common names table, you will find some common names for these things. And these are typically whole things. Okay. So you'll see like calcium oxide is quicklime. Okay. That kind of thing. One of the things you'll see in the ions, and look at our ions, they're up here. If I look like right here, what you see on this one, and this again is not on your list, is it says Mercury 1 or Mercurus. Okay. Sometimes you'll see like Ferris is listed. Some of those are old names. So that was supposed to indicate to us what the charge was. Again, this is old nomenclature. We don't use it anymore because it's much better to just indicate what the charge is on that particular species rather than expecting you to remember what that name means. So we don't do that anymore. But you may see that. Now, if you see that and you don't know what it means, it is always possible to use the inspection rule. But if you know those terms, that's okay. If you use them, I will grade them. It's not a big deal. I know how to Google things so I can find it. It's not a problem. All right. But I wouldn't recommend it. Okay. If you run into one, it's not on a test because I won't do that to you on a test. If you run into one, Google it. Okay. Understand what you're talking about. So if we have more than one charge, i.e. we're in the middle here somewhere like D, the D block. Iron is in here, he's right here. So he has the possibility of having multiple charges. He can lose 2 electrons, the ones that are in this S group, the 4s. And so then he becomes an Fe2 plus. Okay, so he's this guy right here, Fe2. He can also lose one of the electrons that's in here. If you look at your Gs, he has 1, 2, 3, 4, 5, 6. And remember, we talked about if he has 5 in that D block, he has particular stability because it's half full. So he might lose 1 out of that and the 2 out of the S group to be a 3 plus. Okay, that gives him a lot of stability. So he might be an iron 3, and that's what we see with this. Okay, so that name should include the charge. So that's some of the rules we have for that. Now, what does that look like? Well, let's do some practice with that. So we want to name these molecules that I have given you here. All right. So first one that we're looking at is an Rb2O. So Rb2O, Rb being a +1 charge, and I know it's +1 because oxygen is always -2. So if Rb has 2 of them, it must be a +1 charge. Therefore, he should be in this group, which, oh, he's right there. So he's rubidium. So I write the name rubidium. First thing in there gets his name written down first, rubidium. And then we write the name of the second thing, which is an oxygen, but it doesn't state oxygen, it's an oxide. Now, since rubidium only ever has the 1 charge, the +1, we don't have to indicate anything else. He's a main group element, so we don't need to indicate his charge. That's it. That's all we need to do for that. Okay. when we look at our second, I can look at this and I can say, okay, calcium is Ca. Calcium is right here. And I know he's going to be right there because I remember that Br is a halogen. So he has a -1 charge. If he's a -1 and there are 2 of him, that means the calcium has to have a +2 charge. And so he should be an alkaline earth metal. And he is right there. And he's calcium. So we're going to write that down. Calcium. And then we have bromine. Br is bromine. But he's not a bromine. He's a bromide. Because he's the second. And that's all I have to write. The fact that there's a Ca and 2 bromines is dictated by their charges. So I don't have to indicate that. Okay. Next one that we're talking about is Mg and S. So we can find Mg on the table, and that's magnesium. And then we have to find S, and S is over here. He's sulfur, but remember, he becomes a sulfide because he's the second one in there. Magnesium sulfide. And again, I don't need to indicate how many there are because that is determined by those charges. The next one that we have, Na3PO4. Well, I know that Na is on the table. He's right here. He's sodium. So we're going to write sodium. Now, this other thing is in parentheses. So if it's in parentheses, I know it's a polyatomic ion. Polyatomic ions are always on this table that we've been given. Okay, so if we're looking at our exam handouts, common polyatomic ions appear here. And so we've got PO4 that we need to find. So PO4 is right there. It's called phosphate. And you'll see that PO4 has a 3- charge. And that's why I need 3 sodiums to go with it. Okay. But I'm only concerned about its name right now. So sodium and then phosphate. Now, I don't change its name. I just write its name. With the polyatomic ions, that's all I'm going to do. Sodium phosphate. So it doesn't matter what it is in the table. We just write down the name. Okay. Cool. One more that I need to talk. And I'm going to show you how I can do that from here. So the next thing I have is this Zn. Zn. I don't know what that is. Oh, wait, I see Zn. He's zinc. So we'll write down zinc. Zinc. And then I know O is somewhere. He's oxygen, but again, that becomes an oxide. Okay. So again, all I had to do was find them. My metals, I just write down their name. That gets written first. My anions, the negative guys, they get their name, but it gets changed to an IDE unless it's a polyatomic, in which case I just write down the name. Okay, so that's how I go from formula to name. And when we talk about going from name to formula, let's get rid of this for a minute and let's look at tellurium IV chloride. So the fact that it says IV indicates to me that it's probably in here somewhere. So I start looking at the T's. Ti is titanium, so it's not that one. Tc is technetium, it's not that one. Ta is tantalum, I think is how you actually say that. I'm not really sure. That one. That. But that's this one. Now, tellurium. All right, and it indicated that tellurium is a +4. So they told me that Te is +4. So I'm gonna write down that ion. I always write down my ions because it makes it easier for me to write down my formula if I know what they are. The other thing I have is chloride, which means that I'm talking about chlorine, Chlorine picks up 1 electron to become Cl minus. I'm putting together this Te4 plus 4 and the Cl minus. And what I said before was that I would take this plus 4, and that 4 would become the subscript on the Cl, and the 1 would become the subscript on the Te. That would become TeCl4. And there's an implied one here. I don't have to write it, but I can. So TeCl4. Cool. And that's all I need. Manganese 2 phosphate. This is manganese. I'm going to look at my M's. There's manganese right there. So he's Mn. He's a 2 plus. And then I need to find the phosphate. And again, that was one of those polyatomic ions that I had. So I'm going to go back to this list and find that phosphate. And phosphate is right here. And that's a PO4 3 minus. PO4 3 minus. So I need to put together that Mn2 plus and the PO4 3 minus and make that neutral. So the 2 here is going to become the subscript on the phosphate, and the 3 here is going to become the subscript on the Mn. I'm going to write Mn3. PO4 2. So if I multiply the 3 times 2 and 2 times 3 plus 6 minus 6, so we're electrically neutral, therefore Mn3 PO4 2. Okay? 8. That's awesome. I can do that. Now, before I close this out, this next thing that I'm looking at has a nitrate in it. Now, nitrate implies to me that it's got to be in this list because an 8 is not normally something that I see in the periodic table. So that nitrate is this guy right here. He's an NO3 minus. I'm going to write that down. Now I'm going to go back and look at my periodic table. I'm looking for zinc 1. Zinc, probably going to be in here. No, that's zirconium. Oh, zinc, Cn, and he's a plus 1. Because that's what that charge indicates. So Zn plus NO3 minus, that's going to become a ZnNO3. And of course, I don't need to put the parentheses here because they're plus 1 and minus 1, so I know that there's just one of them. But I can include it if I choose to. Either one is correct. So up to you. Right? We have aluminum. Now, aluminum is one of these guys that's kind of weird. He's right here. So he's an Al. He is a metal. So he loses electrons. He loses 1, 2, 3 to become like the nearest noble gas. So he's a 3 plus. And then we have our oxygen. He's right here. He picks up 1, 2 electrons to become like the nearest noble gas, like me. So O2 minus. I put those two together. This 2 becomes the subscript there. 3 becomes the subscript there. So Al2O3 is the formula I end up with for that. Okay, so 3 plus times 2 is 6 plus. 2 minus times 3 is 6 minus 6 and 6. Yeah, plus and minus comes out to be 0. Okay? And then we're going to talk about our calcium bromide. Now, I have a memory that says, wait, calcium bromide, we talked about that right here. We did. And so it's CaBr2. But if I don't remember that, calcium is right here. He's in that second column, so he'll be a Ca2 plus. Bromine, which is the bromide, bromine is right here. He picks up 1 electron to become Br minus. So I end up with a Ca1, because there's 1 there, and then ER, and the 2 becomes a subscript 2. Okay, so look at that. I ended up with CABR2 for both of them. Yay! That means I did it right. Okay, so questions on how I got to any of the names or the formulas based on the names. This takes practice, a ton of it. Right? So again, we're going to ask you to do a ton of homework related to this because you need to be fluent in getting from name to formula and formula to name. Right? This needs to not be guesswork. So I need you to practice this. Okay. Questions on that part of it? Now we're going to talk about naming our molecular compounds. So we needed to talk about the fact that ionic compounds are different than molecular compounds because you needed to know that ionic compounds are made from metals to nonmetals. They're based in the charges, so that's how we form those formulas. And then our molecular compounds are made from nonmetal to nonmetal bonds, and it's not based in the charges, so it can be lots of different things, and they're sharing electrons. So since they could be many different things, we have to indicate how many that there are, right? And that's that molecular formula needs to tell us exactly how many there are. All right. So if I need to know exactly how many there are, then that name needs to reflect that. Okay. So systematic names are the ones you need to know. Now there are some common names. They're in that table that I showed you. All right. You can use those if you want to, but it is not required that you know any of them. Systematic name will never be wrong. Right? So nonmetal to nonmetal bonds can be configured in a number of combinations. To make sure that we are clear which one we use prefixes for each element to denote how many there are. So dihydrogen monoxide. Dihydrogen, so hydrogen indicates H. Di indicates 2. Oxide and mon indicates 1, so that's H2O, or water. It's the other name that we have for that. It's a common name for H2O. Dinitrogen, nitrogen is N, there are 2 of them because of the di. Tetraoxide, oxygen, peroxide, and tetra is 4, N2O4. The prefixes that you need to know are on the next slide. So they're these prefixes. Will I give you these on a test? Actually, no, these are not on a test. I expect you to know these. Why do I expect you to know these? Because they're incredibly important. Okay. For nomenclature, we absolutely have to know what these mean. So I cannot have you referring to this table to figure out what's a hepta, what's a hexa. You have to know that, especially if you're going to take organic chemistry, because you will get bombarded with these. And you need to know how many there are. That needs to be an instantaneous knowledge for you of how many there are. So this one you need to know. So those numbers, mono is 1, di is 2, tri is 3, tetra is 4, penta is 5, hexa is 6, hepta is 7, octa is 8, nona is 9, and deca is 10. Do I like knowing them? No, I don't. I really wish I didn't, but it is absolutely imperative that you know them. Okay, so that you need to know. Okay, now again, compounds containing hydrogen are non-conforming to nomenclature rules. Okay, so some common things that we talk about: CH4, so carbon tetrahydride. H is at the end, hydride, so is also called methane. Silicon tetrahydride is silane. Nitrogen trihydride is ammonia, NH3. Phosphorus trihydride is called phosphine. Dihydrogen oxide is called water. Dihydrogen sulfide is called hydrogen sulfide. Okay. And B2H6, so diboron hexahydride is diborane. Okay, those are typically common names, so they're not, and they're often even in the wrong order. Okay, so typically we would write H first, but sometimes they appear last, and why they do is complicated. It's typically just because we were dealing with common compounds at the time, and we were more focused on the other thing rather than hydrogen. So we put the hydrogen last, and it's not really the way that it should work for those. So you have to understand that some of these rules are broken when we talk about our systematic name nomenclature rules. All right. Hydrogen typically should go first, all right, because he is the metal guy. He comes, in this group, even though he's not a metal, he should come first. Okay, because everything else is over here. So guy on the left should come before the guy on the right. So how you name that is entirely up to you. I'm not going to take points off if you call it ammonia or if you call it nitrogen trihydride. I may ask you what is the other name for ammonia. I might ask you that. I might ask you what the other name for water is. So in that case, you need to be able to tell me what the other name is. Okay. So we'll consider the following cases. I want you to be able to name ionic compounds, main group metal to non-metal or polyatomic. Name the metal and then the non-metal, whether it be a non-metal or a polyatomic ion. Transition metals to non-metal / polyatomic. Name the metal followed by its charge, then name the non-metal or the polyatomic ion. Molecular compounds, non-metal to non-metal bonding. Name the atoms in the order presented. So whatever order they give them to you, that's the order you'll name them. Indicate the number of each using the prefixes that we talked about. We will talk about naming simple acids and bases. Simple bases are named as ionic compounds, okay? So it's going to be like sodium hydroxide, lithium hydroxide, okay? And the hydroxide is the OH minus. It's in your list of polyatomic ions. So if you look, hydroxide is OH minus, okay? So that's when we're talking about that. Simple acids follow the rules that we'll talk about in a few slides. And we'll talk a little bit about hydrates, which are things that have water attached to them. Okay. One of the most common ones that we talk about is one of the ones that appears in this common names list. So we have a couple of them. So washing soda, Na2CO3 has 10 H2Os on it. That's sodium carbonate decahydrate. And then magnesium sulfate heptahydrate is Epsom salt. So there are hydrates on those. And then gypsum, that's a dihydrate. So those are hydrates that we typically talk about. You may be asked to name some of those in terms of common and or systematic names. Okay. All right. So those are the cases that you'll be asked to talk about. Flowcharts are great for me. So I like to present this to you so that you can look at what are we talking about. So if it's an ionic compound, if it's a metal to non-metal bond, then you're going to use the metal. We name the cation, then we name the anion. So the not metal, then the non-metal, and then or the polyatomic ion, and deal with it that way. If it's a main group, then we don't need the charge. If it's a D or an F, then we do need the charge. Okay, so that's what these two talk about. If it's a covalent compound, then it's a non-metal to non-metal bond. So non-ionic, not composed of cations and anions. Typically, only non-metals are present, and it's covalent, non-ionic, and the rules that we just talked about apply, where we say what they are, and then use the prefixes to say how many of each there are. Acids will be defined as something that produces H plus in water. Typically, the hydrogen cation is written first in the formula. If the anion doesn't contain oxygen, we will name it. If the anion does contain oxygen, we won't. Okay. Talk about how we do that in just a bit. Okay. So this one we will do. Questions, comments, problems on that? Sweet. So let's talk about how we would name these. So CS. Okay. We'll find our table. C. Hard to read. C is carbon. We'll write that first. Carbon. There's one. Now, if it's the first thing, I don't have to put the monocarbon. I can. It's not wrong if I do. So it's monocarbon or just carbon. Second thing is S. And S is here. That's sulfur. So, but the second one, I have to include it. Yes, second one's going to go sulfide. PCl5. P is phosphorus. Again, there's only one of them, so just put phosphorus. Again, I can put the mono in front, but it is not required. Then we have chlorine, becomes a chloride, and there are 5 of them. So 5 of them are going to be penta. Fluoride. So penta for 5. CO2. Now, remember C is carbon. And again, it can be monocarbon, but we don't have to. Carbon, oxygen is oxide, and there are 2 of them, so it's di. Okay. Now, looking at N2O. Now, I know that N is nitrogen, but there are 2 of them, so I need to put di nitrogen. And then there's an O, but it is one of them, monoxide. If you just put one O in there, monoxide, that works too. It's not necessarily monooxide, although both are acceptable. Okay. C is carbon. I only have 1, so I can put it as just carbon. And I've got 4, which is tetra. And C is chlorine, but it's chloride. Next thing we have is Se. Se is right here. That's selenium. So selenium. And then Br becomes a bromide. There's 2 of them. Bromide. Okay. So cool with that. Again, it's all about making sure that we've noted the number of them there. The second thing always needs to list how many. Even if it's mono, we have to say that it's mono. Okay? We can leave off the mono from the first one. If it's not mono, we absolutely have to include it. Okay? I'm going to write the formula for the following. Now, aluminum, again, is a metal. Oxygen is a non-metal. So if we're actually not talking about one of these covalent compounds here, aluminum is a metal. He's a 3+ charge. Oxygen is a non-metal. He's a 2- charge. So that becomes an Al2O3. Calcium phosphate. Calcium, again, is a metal. He's a 2+ charge. Ca2+. And our phosphate is one of those polyatomic ions. And if I come look, that phosphate is PO4 3 minus. So Ca3 EO4 in parentheses 2. Now, magnesium, looking at my table, magnesium is here, he's an Mg2 plus. Then oxalate. It's not an oxide, so it's an oxalate, meaning it's in this table somewhere. I got oxalate is right here. That's C2O4 2 minus. C2O4 2 minus. I have a plus 2 and a minus 2. So I can Mg C2O. That's all I have to do. Silver dichromate. Here, things have gotten interesting. So silver is here. Technically, we should know what his charge is. It hasn't said. So since it hasn't said, and because silver is often +1, we're going to assume that he is +1. Is it good to assume? Well, no, not really, but since I didn't get enough information, I'm going to assume that. Now, can he be other charges? Yes, but if it was another charge, they should have told me. So I'm going to assume that it's +1. Now, dichromate is a polyatomic ion. I need to come find dichromate down here. Dichromate is Dr2O7, and it's 2 minus. So I'm going to go Ag2 Cr2O7. That is my silver dichromate. Okay. So I pulled some more of those ionic things back in here to make you write formulas for them. That's kind of rude, but I did do that. Questions, comments, problems on that? I understand. You may not be told which one it is on a test, so you need to be prepared for whatever you get. Okay. Now, let's talk about acids. For now, we are going to define acids as substances that give up H plus in water. In that case, the formulas for acids contain one or more hydrogen atoms and an anion. So things that we can talk about that are acids: HF, HCl, HBr, HI, HCN, and H2S. Those are all, the compounds that we have. They're acids: HF, HCl, HBr, HI, HCN, H2S. Okay? The name on these: hydrogen fluoride, hydrogen chloride, hydrogen bromide, hydrogen iodide, hydrogen cyanide, hydrogen sulfide. That's the molecular compound. When it becomes an acid, we call it hydrofluoric acid, hydrochloric acid, hydrobromic acid, hydroiodic acid, hydrocyanic acid, and hydrosulfuric acid. So hydro because it's got the H on it, sulfuric because it's the S, and it's an acid because it's got that H plus condoning. Okay. When it's given up that proton, so when the H plus comes off of it, we're just having whatever's left is the corresponding anion. So here would be fluoride, so CF minus, fluoride, the Cl minus, bromide, the Br minus, iodide, the I minus, cyanide, the Cn minus, and sulfide, the S2 minus, when it's lost 2 protons. So hydrogen fluoride becomes hydrofluoric acid. Hydrogen chloride becomes hydrochloric acid. So that's the nomenclature on those binary acids. I will expect that you can name the binary acids. Okay. Cool. Now, as far as your test goes, you have some stuff on your test. You have a list of strong acids and strong bases. These are here. Notice all the names are there. Interesting. Strong bases, all the names are there. If you scroll a bit more, you'll find that there are some ionization constants of some weak bases and weak acids, and the names are there. So you may find the names that you need on the test. Go look for them. Use the things that you've been given. You may not understand, you may not be able to get to that name exactly, but if it's on the test, there's no reason you can't just say that's what it is. Now, bases, for now, are defined as compounds that can yield OH minus in solution. NaOH can give us an OH. KOH can give us an OH. BaOH2 can give us an OH. And ammonia can also give us an OH. We haven't balanced equations yet, but NH3 can react with H2O to give me an OH minus and an NH4 plus. So the production of that OH minus also gives us that OH minus. And so it can act as a base in addition. So those are our bases that we're going to look at. And of course, naming for those bases is just based on what you're looking at. So NaOH is sodium. And then this right here is a hydroxide. This guy is potassium. And then hydroxide. Ba is barium. And then hydroxide. Remember, since these are ionic compounds, we don't need to worry about how many there are. And again, ammonia is a common name for this. So we don't need to worry about its systematic name. If you wanted to give it a systematic name, it would be nitrogen trihydride. And it's hydride because the hydrogen is the second thing on it. So it becomes a hydride, and it's tri because there are three of them. Okay? So that's how we name our bases. Cool. Let's talk about our hydrates. And again, only a few of them that we need to talk about. These are compounds that have a specific number of water molecules that are associated with them. We name the compound and then the number of waters. And so water can be drawn off by heating. The material is called anhydrous if we take the water off of it. So BaCl2 is barium chloride. It normally has two waters on it, so it's dihydrate. Lithium chloride is LiCl, and then it has one water on it, so it's monohydrate. GSO4 is magnesium sulfate, and it's got 7 H2O, so that's a heptahydrate. SrNO3 is strontium nitrate, and there are 4 waters on it, so that's a tetrahydrate. So if I wanted to talk about lithium chloride without any water, we would call that lithium chloride anhydrous because there's no water on it. Okay. So that's our hydrates. Again, usually not an issue, and normally if we're going to talk about one of those, it's in that common names table. So you can find it in one of our common names. Okay. All right. Common names. Again, this is exactly what we're talking about. So things that you might see on the test, you might be asked to refer to this. These are very old terms. So while I understand that we should be moving away from them, again, I was taught these terms and therefore they roll around in my head. It's very difficult for me to get rid of them. Quicklime is a very common term. Ammonia is a very common term. Water is a very common term. So it's difficult for us to unlearn those habits. It's something that we need to consciously try to unlearn, but because it's still stuck in my head, I need to provide you with some way to interpret those terms. And that's why this is here. Okay. Now, I'm just going to introduce organic materials. Now, in the event that you are required and or decide to take organic chemistry refers to anything that contains carbon. Most stuff that we have talked about so far does not contain carbon. And so it's called inorganic because it doesn't contain carbon. Anything that contains carbon is organic. Now, if you ever see me at the grocery store, I will probably be walking through the produce section and spouting off about how I hate those inorganic vegetables. That's because every single vegetable is based in carbon. So it's organic by definition. Now, I understand that the context for the word organic there is different. Please understand that I have some biases against the word that's being used there, and there's a couple of reasons for that. The term organic in the grocery store is a term that you can pay for. That is not a term that is earned. Okay? So if you as a company decide that you want to use that term, all you have to do is apply to use it. Pay a fee to some company that then gives you the right to use that term. It doesn't actually mean anything. So you can claim that it means this, you can claim that it means that, but it doesn't mean anything. Now, a lot of people say that it means that they haven't worked with pesticides. All right. But I can tell you right now that if they successfully brought a product to you, they did some kind of remediation against bugs. They wouldn't have a product if they didn't. Usually that means that they didn't use anything that they consider a chemical to do that. So they've used something natural. It's interesting to me because one of the things that they use that's natural is arsenic, which is one of the deadliest things on the face of the planet. I understand that it's natural, but I also understand that consuming it is really bad for me. And I know that I'm supposed to wash my vegetables. I understand that, but I also understand how difficult it is to wash arsenic off of things. So I get very leery about using chemical, plants that have been treated that way. And it's very difficult for me to know how it's been treated before I buy it. That's why I get nervous about them. One of the other things that I should probably bring to your attention is that sodium chloride is sodium chloride. So it doesn't matter what the salt is, it's sodium chloride. Some salts look different because they contain other things. So Himalayan salt looks different than normal salt because it contains an inclusion. The reason it's pink is because it contains an inclusion, which is arsenic. Okay, again, is it safe for you to consume some amounts of arsenic? Yes, it is. Okay, it's not going to kill you in small doses. But depending on how much salt you use, that can become a problem, and it does build up in your system over time. So while I understand that pink salt is very appealing to some people, and it takes every ounce of me to not say I want it because I love pink. It's one of my favorite things in the universe. I'm not willing to pay the price that might come with it to use it just because it's pink. Okay? For me, it is much better to use sea salt that really doesn't have any inclusions in it. And that's because of the way that it's been recrystallized. They make sure that it has no inclusions in it. Okay. And kosher salts are checked that way to make sure that they have no inclusions in it. And so it's the best I can do. Okay. So be careful with the term organic. Now, organic means that it contains carbon. Hydrocarbons contain only carbon and hydrogen. All right. Anything that has some of those hydrogens replaced with something else, that something else is called a functional group. And it can be a lot of different things. Okay. Some of the functional groups that we often look at are like carboxylic acids or alcohols. All right. So if we look at C2H5OH, that OH group is an alcohol. So ethanol contains an OH group. So that's why it's an alcohol. Okay. We can write those formulas in many different ways. So C2H5OH is the same formula as C2H6O. It's just written in a different fashion. And again, we write them in a different fashion to emphasize different parts of it. So the C2H5OH is written to emphasize the OH group. C2H6O is just written to emphasize how many carbons, how many hydrogens, how many oxygen. Okay? So that's our organic materials FYI, and all I'm going to say about that particular subject. So thank you for letting me spout on organic materials. Now that brings us to the end of our names and formulas. I understand that I am supposed to be going through the in-class practice on the videos, and I really haven't had a chance to do that. There are written keys for you, but I have made a decision to record the lectures rather than going back and doing the in-class practices, because I think it's more important that you get the lectures than the in-class practices. If you want me to go through a particular in-class practice for you, I will be absolutely happy to do it. And I apologize that I haven't been able to do both. So let me know, and I will be happy to address that with you. But there are written out practice, answers for you in D2L. Okay? So that ends 4. I will get this posted shortly. The beginning part you should already have access to, and I will get this tacked onto the end so that you have everything. All right. I will talk to you soon, guys. Thanks.